go through the project. Whoopsies, I'm looking for here we go. Okay, so for the project, one of you was asking what would go in the Excel sheet, yeah? So typically the Excel sheet for the project has something like this. So it has a bunch of worksheets here where you typically would start with the code book. After the code book, you'd have your descriptive, so the means, standard deviations, medians of the kind of key variables, minimum, maximum. You can kind of pull this automatically using the data analysis and just going to descriptive. So it's just the stuff that you get automatically. Correlations, this is just what the correlations are, which again, you would just run correlation over here and that should get you sorted. And then your regression models. So typically your first regression model isn't your final one for reasons that will become clear today. So it's the kind of series of regression models kind of culminating in whatever your final model is, just so I can see the process of how you came to your kind of final model. So yeah, that is what goes in the Excel, and this is fairly straightforward stuff. If it looks roughly like this, you'll get, full marks for that aspect. And for the project itself, it is effectively, yeah, just a slide deck. The key thing, so it's a maximum of 7 slides, including the title slide. Maybe the most important thing is minimize reliance on text. So the less text on your slides, the better. You want graphics, iconography. You want to communicate what needs to be communicated with immediacy and clarity, so as clear as possible. And because this is a presentation that has a managerial audience, you will want to curate the statistics that you show. So like you want to curate thoughtfully but transparently. So expressing correlations in a way that makes it clear what is going on. You I don't think at any point you want to put a p-value on your slides, right? Like no people don't necessarily understand what a p-value is, but the point of it, the fact that it is a genuine effect, that's what you want to get across. That is statistically significant. It is a genuine non-zero effect. Nobody needs to see the p-value. Don't put any tables on your slides. So minimal reliance on text and tables, please. Otherwise, you should be good to go and fairly straightforward. And yeah, a utility analysis or a cost benefit analysis is highly encouraged. And you're gonna want to think about what data should be collected for the next iteration of this, if there were to be one. Yeah. So if someone were to put together a dashboard tracking the issue that you are conducting analysis on, what should go on the dashboard? What new stuff should be collected? In a subsequent data analysis, and are more sophisticated analyses needed, which we'll go through today. The presentation should include notes. Some students like to put their notes, their kind of script in a separate Word document. That's fine. That works. So you can put it in the notes kind of page on PowerPoint or in a Word document. Either is fine. Use of AI is not an issue. Just please put in an AI use statement that'll go up the week before, and like I'm only gonna look at that after the deadline. So yeah, that is pretty much it for the project. It's fairly straightforward. I think I had someone try to come in. No, I think no, I guess not. Yeah, any questions, class, about the project while we're looking at this? Okay, I'm taking that as a no. Okay, if you do have questions, I will be hanging around after today's session to go over anything kind of involving the project or your own project. If you have questions, yeah, that's fine. So I will be doing this today and the next 3 weeks. Basically, at the end of the session, I'll be hanging around to consult regarding the project. I can also meet before, so that's fine. Oh, Alicia's hand was up. Yes,
Yeah,
Alicia.
hey Raj, can you hear me?
Yes, I can.
Yeah, awesome. I just wanted to clarify just something really quickly regarding the text component of this. So
Oh
in
yeah.
the LMS, you gave an example that had the slide deck, I think, or the slide
Hmm.
on a Word document, and then just the kind of like text component
Yeah,
underneath
that's
that.
fine.
So yeah, so something like that is fine. You definitely don't want the text to go on the slide, right?
Yeah, yeah, you got it. So text
Yeah.
off the slide as much as possible.
Yeah. Okay. That's really cool. Thank you.
Yeah, no worries. Anything else?
No.
All good. If not class, let's continue on to the quiz. So quiz marks are out, hackathon marks are out. I will email everyone with the kind of feedback on your specific hackathon slides, but the marks are all up. Shall we go through the quiz together? I will be handing back everyone's quiz when we meet again next week. Okay, so let's go over the quiz class. Question one, which of the following statements about data sets is true? Let's go kind of option by option. Option A, it is inappropriate to analyze data that were collected by somebody else. Is this true? Oh, I see a hand up, Alicia.
No, not me.
Oh,
Sorry.
okay. You're fine.
Sorry.
Okay. Did anyone want to respond to this? Whether it is inappropriate to analyze data collected by somebody else?
Yes.
Why would it be inappropriate?
Oh, I think it is appropriate. Sorry.
Oh, it is appropriate. Yeah. Yeah, it's fine. This is secondary data. Yeah, like it's fine to work with other people's data. And we call that secondary data. There are it's not always perfect, but it's fine. Okay. Next one. Data sets contain a rectangular matrix of variables and observations. Yeah, this is true. So this is the answer. The answer was B. Next, we have combining separate data sets is bad statistical practice. It's not. It's data fusion, right? So you're putting pieces together from various data sets to compose a kind of fused combined data set that is hopefully pulling together lots of different information that can be useful in your modeling. And lastly, datasets can only contain numerical values. You would have seen numerous examples of datasets in this class that had non-numerical values in there. Yeah, nominal data is just fine. Okay, so for one, the correct answer was B. For two, again, let's go question by question. Researchers commit sampling error when they make mistakes in their sampling strategy. This one tripped up many of you. This was quite a distractor for quite a few of you. So the thing about error in a data analysis context, error does not mean mistake. Error means discrepancy. There's a discrepancy between your sample mean and your population mean. That discrepancy is the sampling error. Sorry, it's the estimation error. The aspect of that that's due to chance is the sampling error. Yeah, so this is A is false. That's not the correct answer. The sample size refers to the number of variables in the dataset. This tripped up a few of you as well. It's the number of observations, not the number of variables. Yeah. Samples differ from each other by chance. This is true. This is straight up true. Samples always have the same mean as the population. No, not true. So the answer to this was C. Which of the following statements about variables is true? I don't think we need to go through all of these, but yeah, tell me if there's a specific option you want us to go through. The correct answer, by the way, is C. It is C. Did anyone want to ask about the other options? A, B, or D? Oh, okay. B is quite straightforward. We do this fairly often. Which of the following is most influenced by outliers? It's the mean class. It's the mean. D. Um, You are interested in pharmacists' yearly earnings, so this is the confidence interval question. Yeah, so given a sample of four pharmacists, well, this is their income. What is the standard error of the mean? Now, this is the standard deviation divided by the square root of the sample size. Square root of the sample size, square root of 4 is 2. So 12,000 divided by 2 is 6,000. So that is the correct answer. Yeah, it's 6,000. Bearing, okay, and then so for this question, now we have a sample of 144. Let's form the 95% confidence interval. So again, we apply the formula, right? We go standard deviation divided by square root of the sample size. So that's 12,000 divided by 12, which is 1,000. So our 95 confidence interval is 1.96 standard errors above and below the mean. So 1.96 times 1,000, 1,960. So 1,960 above the mean and 1,960 below the mean. So the correct answer is A in this case. Fairly straightforward stuff that we've kind of gone through quite a bit. There can be opportunities to make mistakes, but more practice will only help. So here we have this vignette from Kiplet Construction. Just one moment, class. I think someone is having trouble coming in. Okay, so we have this vignette here, and all the remaining questions are based on this vignette. So what is the sample size? The sample size here is the number of observations, right? So which migrant workers are more likely to get injured means that the observations are the migrant workers, not the sites, but the migrant workers. How many migrant workers are in the sample? 300. So the sample size is 300, which is an outcome variable, trying to predict injury rates. So injury rates is the outcome variable, A. Stop me if you have questions, by the way. What type of variable is educational attainment? So we know that the options here are primary school, high school, cert or grad dip, uni undergrad, uni postgrad. So these are categories with a rank order. So these are ordinal. These are best understood as ordinal. Then we have the statistic to identify the average for postcode. Postcode is, sorry, did somebody want to ask something? No? Okay. So postcode is nominal. Yeah, like you wouldn't get the average of 6009, 6164. You would just get the one that occurs the most often. So the mode. Yeah, for nominal data, the average is the mode. If you wanted to depict the variation in physical fitness in terms of push-ups, which we know is interval data, yeah, because it's the number of push-ups. It's an interval variable. When you have a variable like that, the histogram is most appropriate to show the variation in an interval variable. For here we have workers' heights, another interval variable, but this time you're interested in the quartiles, which are the cumulative relative frequencies, and that's shown in the ogive. So that's D, the ogive. For number 13, if you want to see whether tall workers have more injuries, you need a graph for showing how two variables fit together, two interval variables. So that's a scatter plot. Which of the following statements about hypothesis testing is true? It isn't A, because when the p-value, we reject the null when the p-value is less than alpha. This is true. Sorry, a false negative, my mistake. So when you lack statistical power, you run a higher risk of false negatives, where you say that there is no effect when there is one. You say that there is no difference when there is one. It is impossible to simultaneously reject both hypotheses. The way hypothesis testing goes in statistics is we've set it up so that it's one or the other. You either reject it or you don't. A smaller alpha level reduces the risk of type 1 error. That is true. So the kind of, if you want to be extra sure, then you go with p less than 0.005. Yeah, you're extra sure. Which of the following are true about the t-test? It's used to explore differences in population means. This is true. So it is A. Just on B, paired samples t-tests are substantially more powerful class. And it is possible to convert data from independent samples into paired samples with matching. If you have multiple groups, you'll have to use an ANOVA and not a t-test. For 16 to 18, we're looking at this figure here, output here. And let's see which of the options in item 16 is correct. Data set 1 and 2 have an equal number of observations. That's not true because there's 7 in 1, 5 in 2. The sample means cannot be determined from the results above. Nope, they're right there. The means are right there. The null hypothesis is that there is no mean difference. Yeah, that's right. The total sample size is 10. No, it's 12. It's 7 plus 5. It's 12. So looking at the p-value here for the two-tailed test, or even for the one-tailed, it's not statistically significant. So it's not significant, and that means that the means are indistinguishable. Their difference is, we cannot say that the difference is non-zero. We can't be certain. And then we have here the difference in means in units of standard errors. Now we know that that is the test statistic, the t statistic. So that is the difference in units of standard errors. So it's A. Okay, now we want to compare the number of passengers per week across 3 different train lines. 3 groups, comparing 3 groups. It's the number of passengers per week. So this is a one-way ANOVA, which we use for comparing 3 groups and for outcomes that are interval, the number of passengers. If you want to test whether proportions are equal, you use a chi-square because your data are nominal. It's male or female. Yeah. What would cluster sampling look like in the context of the Kiplet construction study? So like I said, for all of my short answer questions, 1 sentence is enough. You can go on to 3, and it's fine. It's welcome if you want to go that long, but 1 is enough. So the 1 sentence answer is that you would sample from a randomly selected set of work sites. That's it. Or you would sample from work sites. If you mention that you're going to sample from work sites, you get full marks. You get the full 2.5. If your answer is kind of close, you get either 2 marks or 1.5 mark. Just about all of you got at least 1 mark here. Many of you got 1.5. Many of you got full marks. But yeah, that's it. Cluster sampling is you're sampling by a cluster that already exists. You're not creating a new cluster based on, like, I don't know, say you're creating a new cluster based on postcode. The cluster is the work sites they're at, because that's like, rather than randomly sampling randomly selected groups of people, you go, look, I've got 86 sites. Let me randomly pick 10 sites. And that's my kind of random sampling. Not exactly, but it's a close approximation. That is cluster sampling. You're going, let's pick a bunch of sites and then get all the workers from there, rather than let's get 300 workers scattered representing every single site, proportionally speaking. Yeah, so 1 sentence, simple answer. Benefits of having a large sample size. Okay, so many of you answered that the benefit of having a large sample size is that the sample mean is closer to the population mean, or the sample is more similar to the population. Not necessarily, right? The benefit of a sample size, there are many. A couple of the obvious ones are you're just much more sure of what the population mean is, right? You have a tighter confidence interval. That's one. And that would be enough for full marks. The other is more statistical power. So if you just said that, you're good. Yeah, you get the full marks. The way I mark short answers is fairly generous. I'm not looking for reasons to mark you down. I'm looking for reasons to mark you up. So if you show me that somewhere in your, some of you have rambly answers. If somewhere in your rambling answer you show that you understand, you get the full mark. Yeah, so many of you did get full marks for the short answer. And yeah, so all of your marks should be up on LMS. I have everyone's quiz scripts with me, and I will hand them back next week. And you can hold on to them and revise for the final exam with them if you want. The final exam is going to have similar structure with multiple choice and short answer, but the proportions are flipped. So the final exam will be 20% multiple choice, 80% short answer.
Wait, Raj, can I just ask a question? So I'm
Yeah,
looking at
please.
the grade section. The final exam is split into two different parts. There's one part A, multiple choice, and then the part B is online. Was it both in person?
Oh, yeah, no, it's all face to face.
Oh,
There's no
okay.
online bit.
Oh,
Yeah, there's no
perfect.
online bit.
Perfect.
It's
Okay.
confusing.
Yeah, so it's a 2 hour exam. You get one final exam sheet. The first 15 questions are multiple choice. And then there's like 4 pages of short answer kind of. And again, same, it's exactly the same of answer in 3 sentences or fewer. Here's a vignette, here's some questions. Answer in 3 sentences or fewer. No analysis needs to be done. I will give you the output and you just make sense of it.
All right, perfect. Thanks.
Yeah, that's it on the quiz. Questions. I will also take reactions, by the way. If you reckon any of the questions are not clearly worded enough or something is confusing, I'm happy to kind of uh drop the item, give everyone marks for the item. This has happened before. I kind of see this as part of the testing process. Is if there's something wrong with the test, we make adjustments. If not, yeah, that is it for the quiz. Congratulations to the, I think, 5 or 6 of you that got a high distinction on the quiz. Well done. Yeah, a fair bit of variation in the quiz. And main thing is this is 20% of the mark. There's another like 80% of marks from other parts of the assessment structure. The project being especially important.
What was the average score? Did you do that?
I haven't computed. LMS normally gives that to me. I haven't pulled up that number yet. No, I don't know. Yeah. I usually check that sort of thing after like end of the trimester.
Okay.
Okay, that is it for the quiz. Uh, okay. Class, car listings. How did we go? How did we go?
Are we supposed to do this over the weekend? I don't think I've touched any of this yet.
Okay.
I'll
Me
be
neither.
I'll be
I think
honest too.
we're
I'll be
process.
honest. I didn't do it, Raj. I had three assessments due tonight, so
All
I
good.
didn't get to do
All
them.
Yeah,
good. Oh, there's still
yeah.
due. Yeah, look, no worries, no worries. Can I
Uh,
get a quick show of hands, like who's done it? By the way, no worries if you haven't done it. Like again, the way I've structured this class is I get it, you're all busy. Understandable if you can't get to it. Um, it's always going to be there for your learning.
Yeah.
So let's go through this now. And thank you to those who did it. I see Anita did and Jean. Very good. So, I did I see another hand go up? No. Okay. So car listings. Yeah. So this is data that my wife and I scraped from car listings. Like a week ago. And this is for specifically a car, the Kia Cerato, or as I like to call it, the Cerato. So the Cerato is a fascinating vehicle, heaps of boot space. And so in this vignette, we've got Spengler, yeah, who's trying to sell his Kia Cerato and wants to work out how much to price it for. Yeah, this is a fairly common thing. You're going to sell your car, trying to work out what's a reasonable price. Um, so we've pulled together some data from car sales. Every single Kia Cerato with the S badge on sale in WA. The first thing generally, and this is good practice, do this for your project, is to run the descriptives, get the correlation matrix of all the variables. So you know how to get this let's do the correlation matrix now. It's always worth practicing this. So I'm going to pull up car listings Kia, and let's go and get the correlations. I suppose I should go through what the variables are. Yeah, so the variables are, we have the list price over here in Australian dollars. We have the model year. These are all 2017, I believe, to 2022. This is the number on the odometer that was reported. Notice some are rounded off, some are not. We have whether the seller is private or not. So if it's a dealership, it's a 0. If it's a private seller, it's a 1. Then we have the body type. Those of you who kind of know this vehicle, by the way, Anita, I see your hand up. Did you want to ask something?
No, sorry, that's from before.
Oh, okay, you're fine. You're fine.
Sorry, Raj. If I could, just while we're stopped, I'm trying to download the car listings, and it's a blank document in LMS. I'm just wondering if everyone else is getting a blank document as well, or if maybe it's just a problem at my end.
You got to change the color of the text, Mitch.
Yeah.
Oh
Okay.
no! Oh, it's the text color thing.
So-
Sorry about that. I need to make a note.
Select all the cells and change the text to black, and you'll be fine. I
Oh,
thought the same thing, mate.
Yeah.
You're a magician. All sorted. Thank
Sorry
you.
about that. Okay, I need to make a note.
Same thing happened with one of the other spreadsheets previously. That's the only reason I found it.
Change text color. Very sorry about this. Okay, thank you. Was that Shane?
Yeah, it was.
Yes. Okay.
Yeah, mate,
Thank
it
you.
was.
Thank you. So, okay. The body type, the Cerato comes in sedan or hatchback. So I coded it as a 1 for sedan, 0 for hatchback. Could I have swapped the numbers? Sure, whatever. It doesn't particularly matter as long as one is 1, the other is 0. It's fine. Actually, yeah, you can have it be 300 and 0. It doesn't really matter. It won't affect it'll affect the specific interpretation of this like coefficient, but the rest of the model will be unaffected. And the intercept will be affected. Okay, color blue. So if the car was blue, it's coded 1. If it's not blue, it's 0. Now, what if the car is red? What if the car is black? I made the choice to not code those other colors. I could have if I wanted to. I chose not to. The reason is that Spengler's car in this example is blue. So he wants to know how much to charge for a blue car versus the other cars. Yeah. If you wanted to account for all the other colors, you absolutely could. You could dummy code for all of them, following the dummy coding procedures we covered last week. So choices were made in setting up the data. And when you prepare your own data set, you'll be doing the same thing. Then we have the number of photos here. We pulled this up just from the number of photos on the website. Like, does it matter how many photos there are? Then we have transmission, whether it's automatic or manual. So for those of you who have looked at the data, did anyone notice anything peculiar about one of the variables?
They're all automatic cars.
Spot on. They're all automatic cars. So this variable is useless. You don't need it. So you will occasionally see this in your data where you have a variable for which you expect there to be variance amongst your observations, but there isn't any. They're all the same. And in which case you kind of go, then I can't do anything with this. There's no information in this variable, so just drop it. You don't need it. So this is what we're working with, these variables. So let's look at how they all correlate with each other. So we're going to go data analysis correlations. The input range is, I think we can just highlight that, and that should work. Labels in the first row. Did it work? Yes. Okay. So here we have correlations. So recall, class, that a small correlation, generally speaking, this is like a rough benchmark, 0.1 to 0.3, medium, 0.3 to 0.5, large, is 0.5 and up. And this is roughly, very roughly, the way we interpret this is, okay, let's say we wanted to ask, like what is the correlation between the usage of the car on the odometer and the number of photos. So cars that had a higher usage tended to have fewer photos. And how we find that is we go to either of these. We go to odometer here, go down, and then we find the cell that lines up with photos over here. So photos and odometer. There we go. Too many decimal points. This is a common problem in Excel. With a correlation, generally 2 decimals is more than enough. There we go, minus 0.22. So a small negative correlation where cars that are newer, so higher on the odometer, tend to have fewer that have more usage tend to have fewer photos. More usage, fewer photos. Interesting, yeah. We can look at private sellers. So cars with more on the odometer are more likely to have to be sold by a private seller than not. The correlation is roughly medium and positive. Are you getting the idea here? You're looking at the patterns. When you're running a regression analysis and you see amongst the predictors a correlation of like 0.7, 0.8, you start to worry a little bit that they're very, very similar. Yeah. So here we see list price correlates quite a bit with year and with how much is on the odometer. That makes reasonable sense. But fortunately, amongst the predictors, nothing seems to be correlating too highly, other than, of course, cars that are newer have less usage on the odometer. This makes sense. Yeah, this is perfectly reasonable. Okay, so we now have our correlations. That's good. Yeah, fairly straightforward. Now that we've done that, moving on to the rest of the project, we can run single variable regression analyses one at a time. You can do this if you want. You can do this on your own. But let's just go with the multiple regression, all predictors at once. So let's go to step 3. Let's run our multiple regression now. So let's go to regression. Okay. The Y range is list price. The X range is all of this. That is all fine. Okay, so now we have our regression results. So let's start from the top and take a look. We have, what is of note here? The number of observations is 74. That's correct. There are 74. This is always worth checking to see if there are any issues in just the sample size that's supposed to be there. The adjusted R square is 79%. So we would interpret this as saying that our predictors account for 79% of the variance in list price. So we, of course, know that list price varies amongst all these cars that are being sold, and we can explain 79% of this variance through this combination of predictors. Linear combination, I should say. We ignore the ANOVA. This is worthless. This is not worth looking at. Then we have these results here, where what we look at primarily are the coefficients. Yeah, and we look at the p-values, where the p-values tell us if these are statistically significantly different from 0. So, does the number of photos predict list price? P-value is not statistically significant. It's not less than 0.05. No. The number of photos does not seem to have a meaningful effect on list price. The color, whether it's blue or not blue, does not seem to matter, not statistically significant. The body type, a sedan or hatchback, doesn't seem to be a statistically significant difference either. And by the way, we're treating these variables as a system of predictors. So any overlap, like we saw amongst the correlations, right? Like we saw this pattern of, cars that are sold privately tend to have more on the odometer. That overlap is systematically removed from multiple regression. It does not play a role in the coefficients. All of that shows up in the R square, in the kind of predictive value of the full model, but it's partialed out is the language we use. It's partialed out of these correlation coefficients. So basically, after accounting for everything else, body type is not consequential for list price. Seller, private or not, does not seem to statistically significantly predict list price. So it does not appear to have an effect. Although, if we were to run a single regression, let's do this now, where the only predictor is whether the seller is private or not. This, by the way, is equivalent to a t-test. It is effectively the same. It is statistically significant. So let me clarify. When we have a model of list price and the only thing we treat as a predictor is whether the seller is private or not, that factor does predict list price is statistically significant. We interpret this coefficient as effectively saying that private sellers charge $3,593 less than dealerships for Kia Ceratos in WA, etc., etc. Yeah, so that's what we find here. However, this is not taking into account the context of, private sellers are selling cars with more on the odometer, right? What do we know about what private sellers are selling? So let's look at the pattern of correlations. They tend to be older cars. They tend to have more on the odometer. And they tend to have fewer pictures. So the multiple regression takes these overlaps with, the private seller variable. It takes that into account. And it does this automatically. It does this by virtue of how the matrix algebra is run. Yeah. So in doing this, what we get when we have the full model that takes it into account, partials out that overlap in the variance and goes, what is the relatively pure contribution of seller type accounting for or holding as constant the other predictors? Yeah, and that is, it's not 3,000 anymore. It's only 800. And in fact, it's not statistically significant. If we were to look at the confidence interval, we can be 95% sure it's anywhere between charging $255 more or about $2,000 less. Yeah, so like, not statistically significantly we don't know. We don't know. Yeah. We'll come back to this later. But yes, suffice to say, this does not seem to be a predictor in the context of the full model. Now we get to these factors that are predictors. We have on the odometer a coefficient of minus 0.046, and that is statistically significant. What does that mean? That means for every additional km on the odometer, list price decreases by 4 cents, right? This is a very awkward way to put this. Can anyone think of a more intuitive way to restate this finding? For every additional kilometer on the odometer, list price decreases by 4 cents.
By 4 cents. Yeah. The further you drive, the less value your car is worth.
That is true. What is very helpful, class, especially when you're presenting this in your project, is the units can be whatever you want them to be. So if you want, you can change this to every 10,000 km on the odometer, and then we just increase this accordingly. So the list price decreases by whatever this is times 10,000, which is 4608. Is that right? So it is dollars 4,608.
Could you
There we
call
go.
it? It's the depreciation rate is 4 cents per kilometer.
Yes. The way I would recommend reporting this in a project is to put it in units of 10,000 kilometers rather than per kilometer, because 4 cents is like it's a little too abstract. So maybe thinking in 10,000 kilometers is more concrete, easy to follow. So yeah, for every additional 10,000 km, list price decreases by this. Did I do my maths right?
No, one less.
One, oh, that's it.
460.
460, I figured. Okay, 460.77. Thank you. Thank you. So this is, so when you do this, like you would do the maths with a calculator, not in your head in class. So yes, this is the more easy to follow interpretation. Well, like in an exam, either is fine. I just recommend adjusting the units to be whatever suits interpretation. But yes, this is a genuine effect with that is clearly statistically significant. Then we have the model year. Yeah. So for this again is statistically significant, and this is in units of dollars because it's predicting list price. So for every later model year, list price increases by 854 and 79 cents. So with this information, we can start to put together what is a reasonable price. Now, the issue is the intercept. The intercept, recall, is the value, the list price when every single variable is zero. Yeah, so when there's zero photos, when the car is not blue, for cars that are not sedans, that are hatchbacks, for cars that are sold by dealerships, for cars that have zero on the odometer, and for cars in the year zero, AD, which is not super interpretable. So what I advise quite often is to redo the year variable and do years since 2017.
Do it since 2000. It's nice and easy.
Yeah, that works. So the issue there is you get a sorry, did you say 2000?
I did it at 2000, yeah, because then you can still have 22, 21, 19. And when you ask us to do questions based on a year, we can just put the last numbers in.
Yeah, sure. Happy to do that. So like it truly is up to you how you want to rescale this variable. But yeah, year since 2000 works in this instance. So we just rerun the regression. Our X range is changed. We're going to highlight all this. Go. Please don't include year and year since 2000. They are identical variables. Their correlation is exactly one. Don't put both in. And here we go. So now we have an intercept that makes more sense. So this is for a Kia Cerato in the year 2000. And then for every additional year since then, you would kind of add to you would be adding $854, subtract 4 cents for every km on the odometer, so on and so forth. But yeah, that is the idea. So when we did anyone go through this and notice what the difference was between the single regressions and the multiple regressions? The main one was private seller. Yeah, so private seller was predicting list price on its own, but not in the context of other factors. Yeah. And then of course we did this already. We put together our full predictive equation of list price, which is the intercept plus the number of years since 2000 multiplied by this number, and then the number of kilometers on the odometer multiplied by this number. And that gives you the regression equation, taking out factors that are not statistically significant, in which case the kind of final list price for Spengler's Kia Cerato, model year 2020. So let's do this. So the model year is 2020. So 20 years since 2000. The amount, the kilometers on the odometer is 63,000. 63,000 km. And we ignore the rest because none of the other factors were statistically significant. So this is all we need to put together our predictive model. So predicted price for Spengler, this is the intercept plus 20 years since the year 2000. That's how we rescale this variable. And we multiply this by that plus the amount on the odometer multiplied by the coefficient for the odometer. And there you go. So Spengler should be, based on the details for his car, the price that the market can bear is $20,600, give or take. Corey.
I was following along pretty good because I didn't do this exercise. Why did you rescale the year? Because it was in a negative coefficient for the intercept? Is that correct?
So we rescaled the year because the old, okay, let's pull up what it was before. So what the intercept was before was, was it here? Here, okay. It was negative 170,031.61.805. Now we can actually use this still. It just gets overly convoluted. And when the numbers are this big, you can get rounding errors that can somewhat complicate things. Suffice to say, this intercept is tough to interpret because it is the list price when all the variables are zero, and in this case, that is a year zero. So like literally year zero. 0 AD, which doesn't make sense, and leaves us with an intercept we can't use. So we have changed the way we scaled year to give us an intercept that makes a little more sense. One thing you can choose to do, by the way, because the car is a 2020 car that Spengler is trying to sell, you can make the year since 2020, and some are positive and some are negative, and that just makes things easy for you, right? Because then it's kind of the like it's the 0 point is exactly at where your car is, where Spengler's car is, so that's perfectly fine. I want you to feel empowered to change variables and tweak them and rescale them to suit what you want to do. If that helps you interpret, the intercept tends to be not super useful to interpret on its own, and generally the main role it serves is to help you put together the predicted price for a specific kind of observation for a specific purpose. Otherwise, you would just look at the coefficients.
And what was the formula you built since 2022? Can you go to that formula?
Let's do that now. I think that was sheet. Yeah, here we go. So the formula was, we got the intercept plus years since 2020 multiplied by, because it's a 2020 Cerato. So 20 times years since 2000. Yeah, and then we know for every extra km on the odometer, it's 4 cents cheaper, 4.6 cents. So we multiplied the number of kilometers by that coefficient. and add it all up, and you get this nice value here. That is the regression equation. Nat, go ahead.
Yeah, just on this, is there any? Oh, hang on. Can you guys?
There seems to be an echo.
Yeah, sorry, that's a few of us in the class.
Ah, okay. Yeah, sure.
Are there any like things that you really can't do with the changing of the year?
Yeah, what?
Any no-nos that are really going to stuff your data or give you a
Not really. I gotta say, not
number?
really. As long as you are
That comes
aware of.
Yeah, it's just a guidebook on what you can and can't do when you're changing that intercept.
No worries. The main thing is that incrementing your variables by 1 should make sense as much as possible. Yeah. So what do I mean by this? Let's look at the raw data. If the odometer value here were to increase by 1, that's 1 extra kilometer. That makes sense. If seller private were to go from 0 to 1, that means it's not a dealership car, it's a private car. That makes sense. Yeah. Sedan, you go from 0 to 1, that's 0 is hatchback, 1 is sedan. When you increment the value by 1, it should make sense. When you deviate from that and kind of go with kind of wackier rescalings, it makes it harder to interpret. Oddly enough, it doesn't really affect the regression model as much as you'd think, but it does affect how you interpret them. So yeah, that is the main bit of advice, is every increment from 0 to 1, from 1 to 2 should make sense. And for dummy variables, it's only 0 and 1. So that's simple. Yeah. That's pretty much it. Rescale it in ways where every increment still makes sense, but kind of moving things to have a different starting point. No big issues. Oh, and one more thing. Try to avoid blowing out your intercept like this, or ending up with like super high or super small coefficients. You get rounding errors. So, like, I was involved in this project where they were looking at like they wanted to work out which factors made people more satisfied with Alexa devices. Yeah. And they had this like, based on the reviews, they put together this text analysis kind of modeling of like, this is how satisfied I was based on the review I wrote, kind of thing. But the number that was produced, when I would run the regressions, I would get coefficients that are like 0.000, blah, blah, blah. When you end up with coefficients that small, your variable should be rescaled because you bump into rounding error, and rounding error can stuff things up quite easily. So stuff in this range is fine, right? In the hundreds, thousands, 0.002, that sort of thing is okay. But once you get to like this sort of coefficient, or your intercept is blown out like this, I recommend rescaling something. So what I did was I just multiplied their kind of customer satisfaction variable by, I think I multiplied it by 400 or 500 or something, and it was fine. Then it was no longer as blown out as before. You can do this. This is something that you can choose to do, and you just have to justify your choices, show that it makes sense, that it doesn't affect the interpretation. Okay, that's the. I guess that's my survival guide for rescaling. Anything else, class, you wanted to talk about regarding this exercise?
Now hand up.
Yeah. Yes.
Just talk.
Raj, just when you did the price estimate for the exercise, so you excluded the private seller and stuff because they weren't statistically significant?
Yes.
Okay, cool.
Yes. You can choose to include them. the only thing is you don't know if it's biasing your results one way or another because you're not confident that they're genuine, right? If you were confident, that would be a different story. The case of private seller is special, and we'll come back to this actually now. If we're done with the car listings for now, I want to move on to power analysis because this has come up repeatedly from like week 3, where you want to know what's the right sample size for what you want to do. This is the thing that's going to help you the most. Yeah. I recommend this calculator. The formula that Daniel Soper uses is it's an established formula by Cohen back in the 80s. So this is uh, it's good established stuff. And the way it works, I think I have this open already, is with power, you're trading off a bunch of things. You're trading off the size of the model, you're trading off how big of an effect you're trying to find, you're trading off how sure you want to be, how confident you want to be, the power you're looking for. So when you do this for yourself, the power level should not change. Just leave it at 0.8. This is just default. When I am doing stuff, when I am doing stuff that is like paid consultancy, I like to make this 0.9 to be extra sure of finding effects if they are there. But 0.8 is adequate. Probability level 0.05 is pretty standard. I generally don't change that. Then here we have the number of predictors and the anticipated effect size. Class, let's do a power analysis now for the car listings project. Yeah. So how many predictors did we have in our car listings model? We had in our data 1, 2, sorry, this is an outcome variable. So our predictors are 1, 2, I'm double counting. 1, 2, 3, 4, 5, 6. 6 predictors. So let's put in 6 predictors here. How big of an effect are we looking for? Now, when we hover over this question mark, it gives us the conventional eta squared. You don't need to know this, but the conventional numbers for what is a small effect, a medium effect, and a large effect. And let's go through like some benchmarks of what that means. Yeah. So here are examples based on kind of data that are out there of what are quote unquote large, medium, and small effects. Yeah. So a large effect is that men are taller than women on average. That's a fairly large, obvious, glaringly obvious effect that you don't like. If you are an alien who has not seen humans and you don't need to see a lot of humans to kind of work out, yeah, men tend to be taller than women. A somewhat smaller effect, a medium-large effect, is that women own more shoes than men on average. Medium effect, for example, people who like spicy food more likely to enjoy Indian food on average. Not true for everyone, but you do tend to see it. And then I went and I looked at our Airbnb data and I worked out the effect size for the difference in price for Bustleton and Bunbury listings. And it was a medium effect size. So that difference in price, that would be a medium effect. A small to medium effect size, as men are heavier than women on average. It's not like that's not always true. There are heaps and heaps of exceptions, right? But like on average, kind of, yeah, there is this small to medium effect. And then a small effect is that Dutch men are taller than German men on average. So I think the difference is something like 2.5 centimeters, which is not very noticeable, but it is a real and stable effect. It's a genuine effect, but it's small and it's subtle. So when you are working out what you're trying to do, are you looking for glaringly obvious men are taller than women effects, or are you looking for very subtle, very delicate and difficult to find effects like height difference between Dutch men and German men? Yeah. The smaller the effect you're looking for, the bigger the sample size you need. So hopping back to our power analysis, yeah, shall we stick to a medium effect size class, or would you prefer small to medium, medium to large? Like, how big of an effect would you want for the car listings project?
Medium.
Medium. Okay, let's stick to medium. Okay, let's calculate. Let's run this. It tells us that the minimum required sample size, if we want the medium effect, is 97. So we actually, with our sample, we don't have enough power to find effects. So hopping back to what we had in car listings, hopping back to the results for seller private, it might be that we have a false negative here. We're saying that there is no effect of seller, but it might be because we lack the power to find effects if they really are there. Yeah, we need 97 cars. And frankly, there just aren't that many cars, right? I literally, this is every car currently on car listings. Maybe if I had sampled from kind of going back 3 years, it would be a different story. But I looked at everything that was on sale this like just last week. So yeah, we actually don't have enough. So what if we kind of go, okay, how do we adjust this? Maybe we be okay with a smaller model. Let's see what happens if we drop the number of predictors down to 4. Let's kind of simplify, make the model more sparse is the language we use, a sparser model. With 4 predictors, 84. Okay, we still don't have enough. Maybe what if we go to 2? 67. Okay, now we have enough, but our model has shrunk a lot. Yeah. Let's go back to our full 6 predictor model and let's go, okay, we can't find medium effects. What if we can just be okay with medium to large effects, something like a 0.25? 61. Now we have enough. So then we kind of go, okay, so we can have all these predictors in, but just so you know, we can only find like effects that are medium to large and trust that they are genuine. Yeah. So in the kind of ballpark of the difference in the number of shoes between men and women, that kind of thing. I think another medium to large effect was the temperature difference in Perth from February to March, that it gets that it gets colder. And it's colder in March than in February. That is also a medium to large effect, right? So when you are setting out with your projects, you're going to want to work out how small of an effect is enough, right? There are instances where you want small effects because you're dealing with say a lot of people, a lot of observations. Small effects add up; they really matter. Then you're going to want to increase your sample size, adjust your model accordingly. And kind of in the case we have here, we kind of have to shrug our shoulders and just say, all we can hope to really show are medium to large effects. It might be that the effect of seller type is smaller than this. It's in the small to medium or maybe medium, and we just don't have enough power to find these effects. In my consulting, I make this clear from the outset before I run any analysis is I go, this is the smallest effect size of interest is a small to medium effect or a medium effect. There might be smaller effects in the data that we work with. I won't be able to find them. And anyway, these are maybe not worth spending your money on because, well, they're small to medium. Yeah, they're less, they're consequential, but they're less consequential. Yeah. So these are the kinds of trade-offs that you'll be working with. So with your own data, I strongly recommend do a power analysis and kind of see what you can realistically hope to find. Yeah. So with the Kia Cerato data, we can't build a small mousetrap to catch these small effects. All we can hope for are these medium, large, fairly substantial effects. Questions, class, about power analysis? I won't get into how I computed the effect sizes. That's beyond kind of this level of class. But suffice to say, the numbers on the website are pretty reasonable. Okay. Let's continue then. Okay. So that was power analysis. So far, everything we have done is unstandardized regressions. Yeah. So we did our analyses with raw data. And by raw data, I mean just one moment, just clearing up all the sheets I'm not using. Okay, here we go. So it's just the variables in the original metric: list price in dollars, years in unit of years, odometer in kilometers, dummy variables. And this we interpret the way we would for everything we've done so far. Yeah, the B coefficient is it statistically significantly different from zero? Look at the p-value, look at the sign, which only matters if it's statistically significant. And then we interpret this as a 1 unit increase in the predictor is a B unit change in the outcome. So going back to car listings, that is a 1 unit increase in kilometers on the odometer. Predicts a 4.6 cent decrease on average in list price. Straightforward. Now, note that the B coefficient is in the metric of the predictor variable. Yeah. So I'll give you an example here. Here we have an overhead in a factory, yeah, where it's predicted by the number of hours the machine is running and the number of production runs, yeah. We see that for every additional machine hour, overhead goes up by $43. For every additional production run, overhead goes up by $883. They're both statistically significant, and we have this nice regression equation here. The question is, which variable matters more, machine hours or production runs? Which one is the stronger predictor of overhead? Let's bring this question to car listings and look just over here. We have years and we have overhead. Which of these factors matters more for list price? The model year of the car or its usage?
Both.
Sorry?
Both.
Both matter, but which one matters more? Which is the stronger predictor?
The odometer.
If you had to pick one, the odometer. Why do you say that?
Because you can have a car from 2000 but only doing 10,000 Ks. The car will still be newish.
Fair enough. Fair enough. That's a good point. That's a good point. Looking at this, can you kind of tell?
No.
Yeah, not necessarily. Not necessarily, right? Because this is, it's based on kilometers and this is based on years, and those are not they're not commensurable. Yeah. So the way we kind of make things commensurable, everything we've done so far, is we work with z-scores, class. We work with z-scores, and this gives us a standardized regression. So I have here put together a version of the car listings data where I've worked out the z-scores for everything, list price, our outcome, and all the predictors. I haven't rescaled year. Let's not worry about that for now. So I have the z-scores here, and in a standardized regression, you're running analyses on the z-scores. You're running it on the z-scores. Our y range is z price, and our x range is all these standardized z-score predictors. Okay, we have the results. Notice the standard error, the R square is exactly the same. We're still explaining 78.8% of the variance. Now, what's changed is that all of these coefficients they're not B coefficients anymore. Now we call them beta. Yeah, like the Greek letter beta. And these can now be directly compared to work out which has a stronger effect. The way you interpret this is similar to a correlation. Similar, yeah. So here we have odometer minus 0.61, year is 0.43. 0.61 is larger than 0.43, the absolute value. And so we can see that this has the stronger effect, exactly like you said, Mos. And probably for the reasons that you said, yeah, like the usage is more consequential. But yeah, here we can directly compare which effects are bigger than others. And yeah, private is way smaller. And yeah, there you go. If your goal is to work out the relative contribution of variables, you can't do it with the unstandardized regression that we've been running because you're working with different metrics, yeah, odometers on kilometers, years. So when you put them all in the same metric of standard deviations, z-scores, then you get numbers that can be directly compared to work out which is bigger, which is not. So yes, odometer matters more for list price than model year. Sensible. When you do your projects, you may find that you need to do this, depending on what you're asking, depending on the goal of the project. So here, on standardization, it does not affect the p-values, does not affect the r-squared. P-values are entirely unchanged. The only difference is that everything is now in units of standard errors. I will not fuss a lot about the interpretation of the betas. Yeah, the main thing is that the bigger they are, the more they contribute. It's now about the relative contribution of predictors. Yeah, so depending on what you're trying to do, you may find that you'll need to report the standardized rather than the unstandardized. Yeah. This varies so much from project to project. For some projects, unstandardized is the only thing that makes sense. For some, standardized is the only thing that makes sense. For some, you want to have both, where you go, this is how much blah, blah, blah matters for revenue, but like which matters the most, which is the lever that is most important to pull? Oh, it's that one, the other one. So there you go, standardized and unstandardized regressions. How do you do a standardized regression? You use z-scores of the predictors and the outcomes, including dummy variables. Let me make that clear, including dummy variables. And those coefficients are no longer B's, they are now, pardon me, beta coefficients. Questions last about standardization? Yeah, Corey.
What do you mean by dummy variables?
Okay, dummy variables are variables like private seller, 0 or 1. Body of the car, sedan or hatchback, 0 or 1. So when you take a nominal or binary variable and you code it as kind of a mix of zeros and ones, that's called dummy coding. The specific kind of process and details are in last week's lecture, kind of how you dummy code, what are the kind of rules to follow. Yeah, so these dummy variables, as we call them, should also be standard. You should also compute their z-scores if you are running a standardized regression. All right. So anything else on standardized regressions? If not, okay, let's continue. I just want to check that we are still recording. Okay, recording is still going. Okay, good. Okay. Cost benefit analysis. Strongly recommend doing this for your projects. It is genuinely possible that this is the most important thing you take away from the unit, is being able to do this with your regressions. And this is arguably why we do regressions. Yeah. Is taking your predictive model and translating it into kind of the dollar impact of a certain process or intervention. So the way we work out costs and benefits from a regression model is we have this neat little equation here. You have your B coefficient by the number of units multiplied by the number of observations minus the costs. Best way to understand this is with an example. So going back here, we had overhead, yeah? And let's say you have a way to reduce the number of machine hours, this technique to reduce machine hours. Your new technique will require 2 fewer machine hours to run. So doing this will save 2 machine hours per day. So let's put together the cost benefit of doing this. We know that for every extra machine hour, on average, daily overhead increases by $43.54. We know that doing this will reduce machine hours by 2, so 2 units. Yeah. You're doing this in only one factory. Let's say you only have one factory. If you had 5, this would be 5. Where is it? Here. So if you had 5 factories, that would be 5. If you only have 1, so it's 1. Yeah. So 1 in this case. And you figure over the span of a year, if you spread out the cost of doing this, the cost of training people, the cost of any equipment needed, the cost of your time, and you spread that out, that's 25 a day. Yeah, over a year. You can you can amortize this however you like, but suffice to say, you've got your costs. Yeah. Um, Here, how do I get this taskbar to go away? I'm just gonna, whoops. Let me just fix my PowerPoint. Okay, now it should be fixed and you should be able to see everything. Sharing screen again. Whoops. No, wrong screen. Sharing screen. Okay, we're back. So, going back. Okay, so we'll do the maths. And I did this earlier, so these should hopefully be correct. $43.54, that's your beta. Sorry, your B, which we got from here. Yeah, that's your B coefficient that you got from your modeling. You know it's going to save you 2 hours. 2, you're doing this in 1 factory. 1, you multiply all this. That's the benefit per day. The cost per day is $25. Do all the maths, you get $62.08 per day saved, or $15,520 per year, assuming you're running it for 250 days. That is the cost benefit analysis using unstandardized regressions. And again, this works because your outcome is already in units of dollars. So if your outcome is like overhead, revenue, earnings, whatever, then this works great. Questions about this easy version of cost benefit analysis?
Would we be getting a question like this in the exam?
Simplified version of this. I won't ask you to kind of do the maths, but I will kind of ask about how this works roughly.
Okay, thanks.
Yeah. Sure. So that's the easy version. Now, not every outcome variable is in units of dollars. Oh, sorry. Corey had a question. Corey, go ahead.
Is it easy? Like you said, it was easier. You can it's easier to work with this cost plus because your units of measurement are all in dollars, correct?
Your outcome specifically. If your outcome is in units of dollars, overhead, revenue, debt, yeah, anything that's in dollars, this is easier.
So if you were working on a study, you're trying to get your units of measurements of your variables to some sort of rate of units per dollar, that would be the easiest, right? And then you don't have to use this. You could use it standardized, right? Or unstandardized.
Yeah, so you would do this unstandardized if it's already in dollars. If it's not in dollars, you'd have to use this other version. So this is what you would use for outcomes that are like work performance is a classic one. Retention, absences, project delays, customer satisfaction, net promoter scores, like anything that is important, that is valued, but is not in units of dollars, you would need to make adjustments. Yeah. Now, what we do in this instance is we do something based on standardized regressions, not unstandardized. And the way we do this, it's kind of neat, is you get the beta. So how much does your predictor predict your outcome? And this is in units of standard deviations. Yeah. And then we multiply that by this thing that requires a little bit of guesswork. This is something you never know with precision, but you can kind of guess what this is. SDY is the standard deviation of your outcome in dollars. So if your outcome is work performance, this is what is the added value that an above average worker, someone who's 1 standard deviation above the mean in performance, what is their added value to the firm in dollars? Rough estimate of what that is. Now, when we do this conventionally, we assume that it's 40% of annual pay. You can adjust this as you wish. Yeah. But basically, this is you starting to think about, okay, this is my outcome. What is this worth? What is the impact of this? An above average delay, an above average level of retention or loss. What is that worth? How many observations will be affected, and then the costs. So working through an example here, classic one, using IQ testing to hire grads for your grad program. Let's implement the formula here. We know in the literature that grads whose IQs are 1 standard deviation above average tend to perform 0.31 standard deviations above average. Kind of see this again and again. So 0.31 is the beta. That's, again, just to remind you what that is exactly. That is this. Yeah, that is using the Z scores to predict the Z score of list price. In this case, it's 0.61 for odometer. Yeah. Going back to our example here, it's 0.31 for IQ to performance. Yeah. And then you work out that an above average grad brings in $30,000 more value. You can do this based on the 40% metric. You can do this by asking managers of these grads, like, hey, how much does someone above average bring? Like, what is their value in terms of money saved, in terms of work that gets done, and so on and so forth, like approximately. And you're hiring 10 grads a year, so this affects 10 individuals. And then you work out that the overall cost spreading over kind of your whole recruitment cycle is $25 per candidate, where the testing is actually $10, and most of the cost is training HR, making sure they're on board, liaising with the IQ test provider, getting that set up, your time, like all of those costs taken into account. You reckon, yeah, approximately $1,000 for the whole thing. It could be more, yeah. But let's assume this for now. And then we do the maths, where the total added value is the beta multiplied by this value, multiplied by the number of people being recruited. That's your benefit, minus the cost. And that gives you the total added value of using this by hiring above average intelligence grads. You get $92,000 a year of value if you were to do this. Yeah. It's not applicable to every project. So I've had people come to me with projects where trying to assign a dollar value to the thing they're trying to predict is just wrong. Like it either doesn't make sense or it's just not right for whatever reason. In which case, don't do it. But if you can, it really elevates a project. And you can incorporate uncertainty. Yeah, where like, what is the value of a high-performing grad? Maybe it's not $30,000. Maybe it's only 10,000. Or maybe the cost is an underestimate. Maybe it's actually 4 times more expensive, $100 a candidate. And then you can kind of show, well, so it kind of varies. The benefit varies from 27,000 a year to 92,000 a year, depending on the assumptions that you make. And you can make assumptions about what the beta is. You can make assumptions about any number of things. Yeah. And incorporate them into your cost benefit or utility analysis. Strongly recommend doing this. You don't have to if it's kind of overly complicated for you, but this is what sets apart the high distinction projects a lot of the time, is they do this and they do it well. Questions about cost benefit analysis, class? Mitch, please. Yeah, go ahead.
Raj, you said earlier that we couldn't use tables, or we shouldn't use tables in the project. But so how would we display this if we were to put it in our project?
Yeah, that's a good question. You can for this sort of thing, the number itself is so consequential that I think this may be the one exception where you would want a table. Or yeah, I don't quite know how you would present this other than as a table. All the other ways I can think of make it harder to understand rather than easier to understand. So you could simplify, you could drop the middle option. You could kind of go offer a range. You can have You could kind of beside the number have like an icon of like 92 is like you have like a square here with 92 kind of cells filled out, and here only 30, so it's cheaper. Something like that, or the table is fine for this. But yeah, that's a perfectly fair question. I think for this sort of thing, a table is understandable.
Cool, thanks.
In student projects in the past, they have not done the table. Some of them just do the utility analysis. I think I saw one that did a table. So look, it's up to you. You can just do the basic utility. I recommend doing the table just kind of for your own benefit. Yeah. Class, any other questions?
Where did
Okay.
Raj go? Oh, there he
Oh,
is.
I'm here. I'm here. Just had a little some green tea. Okay, so it is now 7:30. I know we're doing this online, but I wonder if some of you might want a break. Would you want a break or would you want to power through?
I'm fine with powering through if everyone agrees.
Yeah, likewise.
Powering through, yeah.
Power through.
Got it. Okay, let's go. Goody. So we have now covered most of the basics of multiple regression. Now we get into the assumptions, and this is like, if you've taken like a stats class before, this is the part that's often seen as boring. It's only boring if you don't encounter this, and you will. So just about every single one of you will have data that violates assumptions in a way that you kind of go, oh, should we really be doing regression? This is really the right way to go. And this often opens up opportunities to do interesting things. Yeah, so we'll go through this now. The main set of regression assumptions has to do with so here we have this little acronym LINE, that it's linear, that the errors or the residuals are independent, the residuals are normal, and the residuals are equally spread out. Basically, the residuals are independent and identically distributed, we call it. And then there's a couple of other assumptions that there's no what we call multi-collinearity, where variables overlap too much. Regression also assumes that effects are consistent across observations. And then regression also assumes that you can make causal claims. This will be the topic next week. We're going to go into causal claims. How do we get that cause and effect? And then that everything is measured perfectly, which we'll get into in week 11. So today we're going to go through this. This is simpler than it looks. Yeah, we'll come back to this later. Let's start with linearity. Linear regression. The relationship between X and Y is linear. Like I've been saying from last week, we're trying to work out the optimal linear combination of predictors that kind of model an outcome. But relationships aren't always linear. So you can have your too much of a good thing effect. Classic example of this is so-called choice overload. Yeah, where for those of you who've been to the US, has anyone been to a cheesecake factory? So Cheesecake Factory is this restaurant in the US. I see a couple hands up. Elise, would you like to say, would you like to tell us about Cheesecake Factory? I think I saw Shane's hand go up too. Oh,
sorry,
yeah, Elise, go ahead. Yeah.
Yeah, it was quite a while ago now, but Cheesecake Factory is sort of like a chain franchise, I guess typical American restaurant, kind of formerly cheesecake based, but now there's, like every other American restaurant, there's not much on the menu that you can't get if you want.
It is everything. Yeah, the menus are massive. They're like Can't find anything in my home office that's thick enough. Massive, massive menus. Everything you can think of. They've got steak, pasta, all sorts of desserts, not just cheesecake. So they have everything. So when you go to Cheesecake Factory and you're like, what do I get? It is choice overload. There's so many options you can have. It's overwhelming. And then you can kind of have on the other side places where there's only a few things and you go, well, I kind of wish they had like something else. um like they don't quite have the thing that you like. So with the effect of choice on satisfaction, you're probably better off in the middle, where your menu has enough options to kind of cater to everyone, not too many that it's overwhelming, and not too few that people don't get what they want. Yeah. The way this works out is there's two processes at work. You have the diminishing marginal benefit of more options, where once you get to this many options, you don't get any extra benefit. And then as you have too many options, the costs become overwhelming, and it's like, oh. So you get effects where the relationship isn't a line, but it's this kind of curve. Yeah. Like this is also a curve, that's also a curve. Regression, linear regression, does not model these, not directly. It does indirectly. Yeah. So the way we get around this with linear regression is through a link function. Specifically, for most of these, we begin by adding squared terms to the model. So if you suspect that the effect of a variable might be nonlinear, one common starting point is you run a version of your model with a squared predictor to see what effect that has. And that'll help you pick up a lot of these effects. And there are ways to graph them. So I've put this up on LMS. There's a tool called Quadratic Regression XLS, where when you're doing this with your own data, you can plug in some of the numbers and it'll graph for you. But let's try doing this now, and let's do this with the wine data. Yeah, so you'll recall we have a bunch of variables, wine variables. We have the ABV and price. You'll recall that ABV did not predict price, but maybe the effect is squared. Maybe like there's like a tipping point where the alcohol level is just right, and that's where the price is highest. And more than that, the price drops again. We can model that just by adding a squared term. So what I did was I just literally squared ABV. And we can now run a regression with this. So let's get all of these as predictors. And you can try this on your own just by squaring the variables. And whoopsies, that is the X range, not the Y range. And the Y range is the price. We're trying to predict price. Good. And that's it. There we go. So the way we check for nonlinear, in this case quadratic effects, is we check if the squared term is statistically significant. It's not. So that means it probably does not have an effect. Note class, when you're testing for this, you need to have the original variable and the squared term. So the linear and the square should kind of both be in there. And if when both are in there and the other factors are in there, the squared term is not statistically significant, you go, no, it probably isn't quadratic. It's probably linear. There are other functional forms that you can check, but the standard starting point is quadratic. And if there are kind of more arcane functional forms, you can find them too. Starting with quadratic is nice and prudent. What I find is with the very kind of unusual functional forms, like kind of cubic effects, or more complicated than that, they tend not to be super robust. They tend to be sample specific, and you can't find them outside of the sample, but see how you go. So there you go, class. Your linear regression assumes that the effect is linear. If you have a reason to think the effect is not linear, try probing nonlinear transformations of your variables of interest. You can totally do this and just say, hey, look, I just wanted to check. And that's fine. where, again, quadratic is the place to start. You square it. Next is independence of errors. This is a tricky one. So this is kind of like a regression model is like voting. Yeah, so a lot of us just voted recently. Voting is you have all of your observations are voting on what the effect is, what is the coefficient. Yeah. In the voting process, in a regression model, it assumes that everyone is voting independently. Everyone has got their own opinion and they're making their own votes. However, you can have instances where people are voting in blocks and you think you're counting 50 individual votes, but actually it's just one block of 50 people voting the same way. And then it's no longer a true representation of what kind of everyone's take. It becomes biased by this kind of voting in a block. Regression works the same way, where you have, say, customer satisfaction ratings from 300 customers. And you have this great model predicting satisfaction, but the problem is they're nested in 5 different branches. Some customers went to branch A, B, C, D, E. And let's say branch E sucks. Yeah. All of the residuals of the customers who went to branch E will be biased the same way. In the context of the regression model, they're voting as a block. Yeah. And so you no longer get a kind of independent, unbiased view of how your predictors affect your outcomes. It's all kind of in this, it's affected by the branch they went to. Yeah, there's a clustering effect. Same if you're looking at, say, leadership or performance, but you have employees and work teams. You have doctors nested in hospitals, where some hospitals are better than others. Yeah, you have firm level data, but it's nested in industries and countries. A lot of you come to me with data like this. So some of you will have data where observations are projects, but like 70 projects are with this client, 20 projects are with that client. Or some of you will come to me with data where you have like recordings from like specific sites, but like 50 recordings are from site A, 60 recordings are from site B. Any bias that is specific to that site will show up in everyone's residuals, and they're no longer separate voters. They're now block voters. And we have to account for the fact that they're voting as a block, or we get a biased understanding where what we think is, oh, this predictor has an impact. No, it's just because all of the kind of like that predictor has a lot of overlap with the block they're in, but the cluster they're in. Our Airbnb data, all the analyses we ran with the Airbnb were problematic because of nesting. All of the properties are nested in the various suburbs, where the residual for any given listing will be similar to another listing in the same suburb because it's the same suburb. It has the same issues. Yeah, we have to account for this nesting problem. And the issue here is specifically a false positive. You're much more likely to find an effect and think it's real, but it's just the cluster that people are in. Now, this is very easy to solve if there's only a few clusters. Then you just control for a cluster membership. So in the context of you have a bunch of projects as your observations, and they're nested in clients, you kind of go, okay, who are my 3 biggest clients? A, B, and C. Let's make those 3 dummy variables. And that way we can account for clustering it in under those specific clients, and kind of D becomes everyone else. Yeah, you kind of somewhat mitigate the problem that way. This is impossible to do with the Airbnb data. Yeah, so with the Airbnb data, there are what, 150, 200 suburbs. So let's say it's 150. That means you're making 149 dummy variables, because remember it's K-1. So 150 categories, you need 149 dummy variables. you're not going to have enough power. Remember our power analysis. Yeah. Every dummy variable you add increments this up and up and up and up. So you can't have too many, or you just aren't going to have enough. You aren't going to have enough power to find what you're looking for. So in that case, you have to use a more complex technique called multi-level modeling. Excel can't do this. I have the software that does this quite well. It's something like 1,000 Australian dollars per person is the license for it, and it's called M+. It is quite complex, but in some cases it's absolutely necessary. Like if you're doing research on like military contexts where you have kind of people nested in work units, nested in kind of higher level units, um, patients nested in doctors, nested in hospitals, kind of accounting for this nesting, stuff gets complicated. Things get extra messy when they're cross-classified. So cross-classification is when you've got nesting in two different ways. So going back to the example with projects, you've got projects as your observations, but it's nested in these projects are for client A, client B, client C, but it's also nested in these projects were done by employee A, employee B, employee C. And so it's cross-classified, nested two different ways. Yeah, I once had somebody come kind of was reviewing a report where somebody worked with data that was from a bunch of employees in hotels. So it's kind of nested in hotel, but also nested in kind of region. So this hotel A, B, C, D, but also region A, B, C, D. You can have these hotels in that region. It gets complicated. I have never worked with cross-classified data myself. It is complicated, messy stuff. You need to get an expert if you have cross-classification. Now, what do you do for your project if your data are have this nesting issue? Try if you can to control for the biggest clusters. So whatever the most consequential clusters are, use that. The other way to go is maybe you run your analysis only on a certain couple of clusters. So like with the Airbnb data, I went and I said, let's run regressions with just Bustleton, Bunbury, and Broome. And that way we can control for cluster membership. And there you go. Then the problem kind of goes away. Yeah, it's accounted for. Granted, you've narrowed what your analysis is about, but at least this problem is resolved. I recommend doing some sort of controlling for cluster membership. However, in some cases, you will just have to say, look, these are initial kind of analyses. Multi-level modeling is recommended to be extra sure of what we're finding. This brings us to a question that is very important for many of your projects, is your data could be considered at multiple levels. So in the example of projects, yeah, you have projects that are nested under clients, you have projects that are nested under staff, and you could go, okay, my observations are projects because I want to compare projects and see which projects have different kind of outcomes. Or I could go, oh, no, actually, I want to compare clients. I want to work out which clients are problematic, what predicts problematic clients. And I restructured the data where clients are now the observations. Yeah. Or I kind of go, no, it's the employees I care about, the people who are doing the project, the work teams, let's say. Then, okay, now those become the observations. When you have multi-level data, you must make choices about what the observations are. And these choices shape everything. Yeah. Basically, whatever your question is, that dictates the level at which your observations are, whether it's projects or clients or employees or whatever version. Yeah. In the example, say with kind of employee, like service employees working in different branches, you can look at differences among employees, or you can go at the branch level, look at different branches or days within people. Well, we won't cover that this time. This is important because relationships can change across levels class. So one kind of classic example is the link between helping and emotion. So when you feel bad, are you more likely to help others? What we find is it's you're both more likely and less likely. So if you are a sad person in general, you are less likely to help other people. So at the person level, people who are sadder than average help less than average. But if we kind of go, okay, some days I'm sad, some days I'm happy, then what we find is the relationship is positive. When on days when you are sad, you help people more than on days in which you are happy. When we change the level of analysis, and we're no longer looking at people, but we're looking at kind of days that we have, the effect changes. Yes, you're going to want to get this level right, whether it's comparing branches, comparing people, comparing clients, etc. One option, this is an option that is open to you, is to look for something called a contextual effect. So this is where you go, okay, I want to predict price of an Airbnb property, but I also want to account for the fact that, oh, these properties are in this expensive suburb. So is it cheap in general, or is it cheap for a property in Dalkeith? Yeah. So what is expensive in the context of a full set of data might be cheap if you go, oh, it's cheap for a property in Dalkeith. We can do this through something called group mean standardization, doing with group mean Z scores. Let me see if I have my example on hand. Do I have a group mean standardization here? Okay. I have Rockingham and Joondalup. So let's say we wanted to run some analysis here to predict price for properties in Rockingham and Joondalup. Now, just offhand, which do you reckon are going to be cheaper, Rockingham or Joondalup?
Rockingham.
Rockingham, yeah. Let's find out. So I think you might have this up on your on LMS, Airbnb group mean standardization. So we're gonna do the first data set, Rockingham, Joondalup. We're gonna pick our Y, which is price. And here we have just the original variables, minimum number of nights, number of reviews, and so on. Okay. So here we have our regression model predicting price of properties, price of Airbnbs in Rockingham and Joondalup. R square is 8%, 8.2%. It's not too bad. We have our dummy variable here called Rockingham, where properties in Rockingham are coded 1 and properties in Joondalup are coded 0. So as we see here, properties in Rockingham are $8 cheaper, but it's not statistically significant, so it doesn't seem to have an effect. The number of reviews is the main thing that seems to count, and the number of listings that the host has. Now, all of these are in general, not accounting for the fact that, you know, maybe it's cheap for a property in Rockingham or expensive for a property in Joondalup. These are effects that are in general rather than specific to the suburb. So we can get around that by computing a different kind of Z score using the group mean. Yeah. So let's do this here. Or rather, we've done this here. I'll show you what was done. This is a set of Z scores standardized by the group mean. What do I mean by this? I went and I calculated the mean for all of these variables for properties in Rockingham and the standard deviation for properties in Rockingham. Same for Joondalup, mean and standard deviation. So what I did was I computed the Z score of every property, not relative to the whole sample, but only to the suburb they're in. So price minus the average, not in general, but the average in Rockingham, divided by the standard deviation, not in general, but just in Rockingham. That is a group mean standardized effect. And so here we have, this is expensive for a property in Rockingham. This is cheap for a property in Rockingham. We have this for a, yeah? And we can do this for all the variables. This property has a lot of reviews for a property in Rockingham. This property has a lot of reviews for a property in Joondalup, so on and so forth. And now we can go, are there effects that are contextual to the suburb? Yeah, contextual, and you can do changes. You can do this with your data, contextual to the client, contextual to kind of whatever thing you're looking at. Yeah, if you're looking at genders, contextual to the gender, let's say. Are you so yeah, now we can run our regression analysis with this contextual variable, and we wouldn't do this with the Rockingham variable. We keep this unchanged. So we run the regression here. Our y range is price. Our contextual standardized price. X is everything else. And there we have it. What we find is not really a lot, actually, but we find this fairly similar, that the number of host listings and the number of reviews still predicts price, more reviews, cheaper. The more host listings, the more expensive. And it's also relative to the suburbs. So if a property has more host listings relative to other Rockingham properties, it's 17 cents more, which is not a lot. Oh, no, standardized. So it's 0.17 standard deviation. So basically, reviews here has a stronger effect. But yeah, that is now group contextualized rather than in general. So if you have clusters where you care about what is the price for a property in this suburb, or yeah, anything that is relative to a cluster, you can use this approach. These contextual effects. Questions class about nesting, independence of errors, group mean standardization. Questions about any of this? Okay. Now we have the normality of the residuals. So many people assume, they hear about the normal distributions and they go, oh, your variables have to be normal to be used in regression modeling. That's not the case. Your predictors don't have to be normal. Your outcome can deviate quite a bit from normality, and it's fine. The main thing is your residuals should be pretty close to normal. Yeah, so the residuals, to remind you, are you run your regression model, you get a predicted outcome, and then you get the distance between what is the predicted score for that observation and the actual score. Yeah, that's the residual. So these residuals should be ideally normally distributed, which is it should be good at predicting for many observations and bad at predicting for only a few. You should not have severe outliers in your kind of residual plot. This is the kind of thing that generally, if there are outliers in your data, it will screw up your regression results. So check for influential values. Yeah. And I want to here draw a distinction between influential observations and outliers. Outliers are observations that are implausible. Yeah, like Airbnb listings that are, say, well over $10,000, even well over $6,000 a night. You kind of go, is this plausible? I don't think it's plausible. These you can safely remove. Yeah. Influential observations are ones that are extreme values, but you go, no, that's possible. It is possible for a listing to be $1,300 a night. Like, yeah, it's extreme, but it's possible. Yeah. So influential observations, what you do with them is you try running the analysis with them and without them using a process called LU, which I'll cover in a bit. Leave one out. You drop an observation, see if that changes your results. This is strongly recommended practice for running regression models. Drop an observation that doesn't seem to fit and then see if anything changes. That is the main thing to do to kind of deal with this risk. And lastly, we have equal variance. This tends not to be a super big deal. This is the issue where the residuals are larger on one end of the variable than on the other end of the variable. Classic example is how much you earn and how much you spend eating out. If you don't earn much money, you generally will not spend a lot eating out. If you earn a lot, then you have the freedom to go, oh, I'm still going to spend a little, or, oh, I'm going to spend a lot eating out. Yeah, so the residual tends to be bigger at the high end, and this can kind of bias results a little bit, but this is like kind of a boogeyman that's not really a genuine, like very big issue. There are standard errors that solve this problem by default. Excel doesn't have them, but most kind of standard software does have quote unquote robust standard errors. So yeah, this is one of the assumptions. You'll see this in your textbook. This tends not to be what I worry about. What I worry about is influential values and outliers, stuff that doesn't make sense. I worry a lot about this. It's nesting, where I am very careful to account for as much nesting as I can, because this can really give you like completely wrong results. And I try to check for nonlinear effects where they seem plausible. Yeah, if they seem plausible, I check for them. If not, generally it's fine. So the way in the textbook to probe a lot of these things is by generating some plots and reading the tea leaves, basically, where you kind of look at the residual plots and they should all kind of be in a straight line. They shouldn't be kind of wiggly like this. So let's pull out some of these plots. You can tell from the way I'm speaking, I ignore these plots. These are not really helpful, but hey, I'll show you what they are just so you know. So let's go back and run our regression here with the car listings data. So car listings, regression with the raw data. This seems right. The X variable is, no, hold on, I have to do this again. So the Y variable is like so. X variable is strange. Huh, all my data disappeared. Oh, okay. Let's see. X range is okay. Okay, now we have our regression as normal. Let's tick all the boxes here. Residuals, standardized residuals, plots, residual plots, line fit plots. Just tick all the boxes, which we did not tick before. And we get our regression results. We now get the residuals for every single one of the cars. So for all 74 cars, it works out the predicted list price for the car. It shows you the gap between the predicted list price and the actual price. So this, for the first car, it was off by only $86. Pretty good model. And yeah, there you go. That is probably the most useful to kind of go and see which are the cars that are not predicted well by the model. So this car 25, is it looks like it is 1,907. Is it more? I think it's 1,907 less. Sorry, 1,907 less than the list price. So this car is being sold for way cheaper than is predicted by the model. This car, again, this one is more than is predicted by the model, because we have here again the list price and we have the residual here. So this is very helpful. This bit is helpful. These plots you can take or leave. Let's look together, yeah? So for here we have years since 2000, and we have the residuals. The residuals are kind of spread out over the range from kind of 17 years since 2000 to 22 years. Nothing really notable about this. Odometer residual plot. These are the odometer ranges from low until the highest, 250,000. So there's a quite well-used Serato here. But the residuals are kind of all over, kind of spread reasonably. This is okay. Private seller. Here we have some of that thing, that heteroscedasticity. You see this with dummy variables sometimes, where there's a lot of spread in price and residuals among cars sold by dealers and less. Basically, the model is better at predicting list price for private sellers than for dealers. But it doesn't look super problematic. It looks kind of okay. There's that. Here we have for sedans and hatchbacks, similar thing. The model is very slightly better at predicting list price for hatchbacks than for sedans. Not a huge deal. Here we have for colors, similar idea. Photos, number of photos and the residuals. Seems like a reasonable spread. Yeah, and here we have the line fit plot. In this case, for this specific variable, the list price, the predicted price. This is, yeah, you can, oh, it's not showing the line because of how my screen looks. Let me fix that. Okay. Oh, is it still not showing the lines? Okay, I'll just run it again. Let's run the regression again. And this time we're just looking at the line fit plots. Oh, it's still not really showing a line. Okay, look, fair enough. I never, like I said, I never use this. These line fit plots are not super valuable. And then here we have a normal probability plot. What these numbers are just extreme cases of like observations that are not predicted by the model, where the residuals are very big. So big residual, but it's looks roughly like a straight line. This is reasonably okay. So as you can see, class, this is like very much reading the tea leaves. And even with the experience that I have, kind of like I used to look at these, I don't find a lot of value in these plots. I show them, they're in the textbook, they're maybe handy to know, but yeah, I never use them. Now, one thing I do kind of worry about is multicollinearity. And this is that point from earlier where your predictor variables overlap. This can break your model. In one of my consulting jobs, I was trying to predict retention, and we had a lot of factors to work out, kind of who's kind of a high risk of leaving. And there were all these levers the organization could pull. And when I'd collected the data and ran the models, I started to notice correlations amongst some of my predictors, factors that are like, are you satisfied with your pay? Are you satisfied with your benefits? Are you satisfied with leave allowances and so on? Like all of these things. They were overlapping quite a bit, which makes sense, right? Like if you're not satisfied with your pay, you probably also won't be satisfied with career development. Like these things are overlapping, and that makes sense. The problem is the organization I was working with needed to know which lever to pull. Should they focus on career development or focus on pay, base pay, or focus on kind of other benefits. It was a tricky situation. And I will note that I did not rely purely on the numbers in my recommendations. I ensured that we ran focus group discussions to ensure whatever we were finding, we were validating with what people were saying. That's super important. Yeah. So we're validating with qualitative data, always wise to do. But regardless, I'm running the models. I want to work out which is the most consequential. And the models just do not run. Like regression is like, nope. What happened in that case was the variables were overlapping so much, the matrix algebra did not work. So as part of the way regression works, the stuff that happens under the hood, it has to invert a matrix. Yeah, it specifically inverts the X prime X matrix gets inverted. Yeah, now in the process of inverting this matrix of the X variables, if amongst the X variables, you have two variables that are identical or a set of variables that when you put them together, the information amongst these variables is highly overlapping. The example here is dummy coding, right? Like in week 8, some of you were asking, why is it that when we dummy code, here we go. Yeah. So here we have 3 order type options: dine-in, takeaway, and delivery. And some of you were asking, how does the model know what delivery is, that it's the 0, 0? When you dummy code, just to kind of revise, if you have 3 categories, dine-in, takeaway, and delivery, you should only have 2 variables. So in this case, the variables are dine-in, where if it's dine-in, it's 1. If it's not dine-in, it's 0. And then takeaway, where if it's takeaway, it's 1. If it's not takeaway, it's 0. We do not create a third variable for delivery. Why? Because then these 3 variables, dine-in, takeaway, and delivery, would be overlapping. They would overlap in the information they show. Why? Because even if I removed this, you would be able to work out which of the customers did delivery. They're the ones that are 0, 0. Yeah, if they were not dine-in and not takeaway, and there's no other option, they must be delivery. Now, when you put all 3 in your regression model, try this with any of the nominal data that we have kind of over the term of working together. You can try this. It will not run. It will give you some sort of error because the matrix won't invert. Yeah, if you have 3 variables that in reality should work like 2 variables, regression will not work. So that is the kind of severe case of multi-collinearity, yeah, where when variables overlap too much, predictors specifically, when predictors overlap too much, the model won't run, the matrix won't invert. There is a slightly less severe, but still problematic version of this, where if your predictors are correlated at like 0.7, 0.8 with each other, you get often what's called a suppression effect, and that can completely stuff up your results. We're going to talk more about suppression later, so I'll come back to suppression. Suffice to say, what you should be doing when you're running multiple regressions is checking the correlations amongst your predictors and just flagging anything that is over 0.7, flagging correlations that are too high, and just kind of using your head and going, is there redundant information amongst my predictors? If there is, that could be creating the problems that I'm seeing. Now, the typical solution when you have multi-collinearity, where correlations are too high, variables are highly overlapping, is you can drop one of the highly correlated variables because they don't show much independent information anyway. They're highly correlated, so drop one. The other option is to use something called dimension reduction, where you go, okay, these 5 variables are kind of overlapping. Let's put them all in one. In my consulting, that specific project, I couldn't do dimension reduction because they wanted to know which lever to pull. And if I combine 5 different levers, they're like, okay, but what do I do? Right? I want to retain people. What do I do? So I could not use dimension reduction. So I had to use machine learning. Machine learning is overrated, except for this. It is really, really good at this. So if you have an issue where you have a bajillion predictors, you can't keep all of them. You don't have a big enough sample size. You won't have enough power, but you have to figure out which ones to keep. They're overlapping, and you want to pick out which ones are the most important. Machine learning can do this quite well, specifically the lasso. So if you heard me mention the lasso before, that's what this is. Um, it is a machine learning technique for you chuck a bunch of predictors at it and it goes this, 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 this. These are the most important ones. Lasso, ridge regression, elastic net, all in kind of the same ballpark. Most.
If you take these variables manually, wouldn't that be biased in terms of results?
Like omitting variables manually?
Yeah.
Well, that's the great thing is if they're correlated, you can drop either one, right? Because they're whatever the correlation is. Remember how in the car listings data, automatic transmission, they're all automatic, so they're all one. There's no information in the variable. When two variables are correlated at 0.85, there is almost complete overlap in the information carried by those variables. So which one you drop doesn't really matter that much. It matters a little, but not that much. And like, if you kind of want to go, okay, I don't want to decide. I want to let the data tell me what should be dropped, then use lasso. Which, of course, Excel doesn't have lasso. If you've heard of SPSS, that is the simplest bit of software that has lasso. Yeah, very handy stuff. It's a mainstay of the work that I do kind of in practice and consulting. You can't do without it. Because so much of like the stuff people need help with is with predictors that are multicollinear, that are overlapping. Collinear, line, co-line, they're sharing a line, they're overlapping. Yeah, so this overlap is extremely commonplace. When you start analyzing your data and you come to me with issues, 75, 80%, it's going to be because of this. You will see. You will see. So that is a multicollinearity. The last
Raj,
kind of
just on
yes,
that.
please.
Yeah, say you drop one, or even if you like ran it twice, like with either of the correlated variables, if one's more significant than the other, is there a bit of a rule of thumb to err on the side of I don't know, being conservative, or is there any right or wrong way to go if one's giving slightly more significant results than the other?
Analyst discretion. Genuinely, it's a mix of analyst discretion where you would kind of have to. Okay, in a situation like this, you will want to keep the predictor that is more proximal. That like when you think about how this comes a little bit to what Mose was saying earlier about what causes list price. Is it the model year or is it the odometer? In a way, the odometer reading is closer because it's like that is the use of the car that affects its worth and its kind of how much more use you can get out of it. So that is more proximal. So if you had to pick between model year and odometer, you'd pick odometer because you know substantively that it is a more proximal, closer cause of list price. But you need subjective subject matter knowledge to make that call, right? If you don't want to make that call or you don't have subject matter expertise, or the expertise kind of goes both ways, do a lasso. Let the lasso tell you.
All right, thanks.
Yeah, no worries. Any other questions on this? Okay. The last thing I want to go over that's a new technique is interaction effects. So in everything we've done, we have effects on average, the effect of model year on average, the effect of odometer reading on average. But it could be that predictive effects depend on other factors. Yeah. So we ran this regression model last week of ABV on price, where ABV, alcohol by volume, did not predict the price of a wine. But you can kind of go, well, what if it depends on the kind of wine? What if it matters for some wines and not others? we can test this. We can check for what's called an interaction effect. You can do this for your project. And if you were to do this, you wouldn't need a ton of predictors. Just 2 is enough to check for an interaction effect. So here, the idea is that the type of wine becomes something we call a moderator. It moderates the effect of ABV on price, where the effect of ABV on price depends on whether the wine is a red wine or a white wine. And the way we do this is we compute a product term. Basically, we multiply the type of wine by the ABV. So first, we compute z-scores for interaction effects, and we do this only for predictors. So it's partially standardized just for the predictors. And we multiply the predictor, the ABV, we multiply that by the moderator, standardized. And then we run a regression model that has the predictor, the moderator, and your product term. And we check if it's statistically significant. I have put together an example. Here, wine dataset for regression. So I don't know that I'd already done this in what you have, but it's not too difficult to do. So let's work out whether the effect of ABV on price depends on the kind of wine. Maybe it's not an effect on average, but for some wines, yes, we do have an effect. So here I computed the z-score for ABV, fairly simple. Then I computed the z-score for the dummy variable, red wine. Yeah, so I have the z-score here. And then I computed int, the product term. And this is literally, I'll do the formula again, this z-score multiplied by this z-score. Multiply them together, it becomes an interaction term, a product term. So now we can try running a regression model with this product term, and we go, okay, we're trying to predict price. And our predictors are these variables up to 992. Okay, so what did I put in as the predictors? The z-score for alcohol level, the z-score for red or white wine, and the product, literally alcohol times red or white wine. That is all we need, and we run it, and what we get, class, is the effect of alcohol by volume on average is not statistically significant. The effect of the kind of wine by itself is not statistically significant, but the product is statistically significant. Now, how do you interpret this? With these interactions, I recommend not interpreting the coefficients. I recommend graphing. Drawing the diagram is the way to handle that. So here, and you can find this on LMS, is a graph. So what I did was I just entered all the information here, and I literally copied all the information out from the regression results. So I copied this, and I just chucked it into this other Excel formula here. There might be some little changes, but that's the idea. Put in the intercept, and there we go. This is the graph, class. So would anyone care to try interpreting this graph? Before we're under the assumption that, oh no, ABV does not have an effect on price. Actually, it does, but anyone care to try? Price of wine on the y-axis, yes.
Is it that it has more of an effect for red wine than for white wine?
Yes, it does. Specifically, for low alcohol red wines, they tend to be cheaper. Yeah. So the effect of having less alcohol is more consequential for red wines. And it's not that you'll notice for the high alcohol red wines, they cost the same as white wines regardless. It's the low alcohol red wines or red wines that are unique, that are uniquely cheaper. Um, the ones with a below average ABV that are red wines tend to be cheaper. This is something you can do. Pick two variables and you go, you know what? The way they come together, it's not linearly, but multiplicatively. They influence each other, and how that impacts the outcome. You can do this for any number of predictors in your analysis. A lot of my students have a lot of fun going, okay, I'm going to check for interactions amongst these variables and kind of see what they find. Yeah, so you're welcome to do this as part of your project. Students seem to have a lot of fun with this one. And yeah, so these are, so you can modify these and see how you go. If you want to do this and you're having issues with the graphs, come to me and I'm happy to help. That's not an issue. Questions, class, about the interaction effects? Yeah, most.
Can you use this interactive model for example, a project or about HR, making a comparison in departments?
That's a good question. So let's say you have like multiple, so like instead of having it red or white wine, you have like 5 departments kind of thing.
Yeah.
It gets tricky. Basically, that is beyond. I'll say that if you are doing it with a nominal variable that isn't binary, purely binary, like if it's like a dummy coded nominal variable, too complicated for the unit. Like there are ways to do it. It's called multinomial regression. We don't. That is way beyond the scope of what we do. Like I know PhDs who can't do that. Like it's extra complicated. What I would advise if you do this interaction is pick moderators that are interval or that are binary. Yeah, so red or white wine, that works. So with HR data, for example, if there are only 2 departments, then you just go, okay, let's kind of see if the effect differs across the 2 departments. That's okay. If you have 3 or 4 or 5, it gets way too complicated. It becomes multinomial. It's a whole other kind of yeah, way too complex.
Can you, like, if I want to use that, can I do it on, so I have to do it on 2 departments at a time?
Oh, so you would stick to just 2 departments in the data. Or I guess what you could do is white wine is department 1 and red wine is everyone else. You could go that way. Yeah, the trouble with this is you get into like kind of fishing expeditions of let's run every kind of interaction we can think of until we find a p-value, which gets into complications. I would advise do this, but kind of be thoughtful about what you're choosing to compare, like what the moderator is. Department might be a tougher choice. There might be easier variables that you have. Gender, for example, is a classic for this. If you were going to go with the gender binary of, for example, male, female, that works very naturally with this kind of analysis, where you have a predictor, you have an outcome, and you go, does this differ by gender?
Okay, so
very classic.
So you're saying choosing a department, for example, and then make the comparison between male and female within the department.
Oh, so your predictor should ideally still be interval. So if you have a kind of I would recommend doing this with interval level predictors, because department is nominal. It like that nominal data, as you can see, creates all kinds of complications just in the dummy coding side of things. Before we get to everything else, maybe we can have a chat about this when we talk about your project.
Yep.
But okay. Suffice to say, if you do this, I recommend both variables be interval, the predictor and the moderator, where ABV is the predictor and it's moderated. It depends on the wine type. The moderator can be binary. If it is kind of more complicated than that, that's stock. Let's talk.
Okay. Thanks. Sorry, guys.
Oh, no worries. No worries. Anything else? Okay, so that is it for interactions. We have gone through a lot of fairly complicated material, class. You've done well. You've done well. So now we get into data prep. Now we get into the final kind of cleanup. Yeah. Preparing your data can be tough. So I have here a checklist of good practices. I strongly recommend checking the minimum and maximum. Like, you get issues with this fairly often. Where variables aren't coded correctly, just double check this. Like, this seems so basic. Did you guys hear there was this story in the news that like a decade and a half of genetic research is all wrong because they did not check the values of the variables. Like, you know how in Excel, if you enter a value, sometimes it treats it like a date. So it was doing this with the SNPs of various genes and completely transforming them, and it wasn't usable because they didn't check. They didn't check that the variables made sense, that the minimums and maximums, the histograms, they didn't check these basic things. And so 15 years of genetic research gone, right? So please do this. This is so easy to overlook. Classic rookie mistake is to run analysis and not realize, oh, oops, my coding does not make sense. So double check this, please. If you have surveys, compute the averages of, like, you have 5 questions on engagement, average them is generally what we do. I'll explain why in week 11. Create your dummy variables. Again, do this thoughtfully. If you have, let's say, 7 departments, you don't need dummy variables for all the departments because that affects your power. Remember that. So you can just go, okay, I want to look at these 2 departments and versus everyone else. So department 1, department 2, and then everyone else. You can do that. You can dummy code to prioritize and draw out whatever you like. Just you have to justify your choices. And then, importantly, missing data, dealing with missing data. Now, this is a very complex issue because data can be missing for many reasons. We'll not get into the weeds, but suffice to say, missing data is one of these topics that's so complicated, you can do a whole course just on missing data. It is that kind of complex. What makes it tricky is that you can have data that are missing where, let's say, for whatever reason, for this observation, they don't have a kind of a score or a response for that variable. They're just missing. It wasn't put in for whatever reason. Or it can be at the observation level. But for this observation, they have no data past a certain point. You see this with, like, longitudinal data where, like, people don't come back after the first time you kind of get your data from them. Then the next time they're just blank. Yeah. Basically, attrition, dropout. They drop out, and so you only have the data you started with. Excel is fiddly with missing data, class. It will sometimes not run the analysis at all, as you've seen if there's missing data in multiple regression. There are several strategies for dealing with this. The worst strategy is to delete anyone with missing data. Do not do this. Please do not do this. This is bad for many reasons. First is it wastes data. Remember that every observation contributes to your statistical power. It adds to your sample size. Not like you are throwing away power by deleting these observations. It can also distort results if, like, remember how I said that missing data can be missing for reasons. It might be that the reason that there's missing data is because, say, that case was extra complicated, and so it wasn't put in. And so when you delete all the missing, you delete all the complicated cases, and then you end up with a biased sample. So when you delete cases with missing data, there is a risk of biasing your sample on purpose, which is sad and bad. Don't do it. The alternative, which is not great, but it's okay, is mean imputation, where you replace the missing value with the average. Now we know for that observation, what was their actual kind of value for that variable? We don't know. Maybe it's the average, maybe it's not. By putting in the average, you minimize how much that observation affects the regression model for that variable. That's why we do it. It's minimizing the impact of that specific bit of missing data. It's not optimal. It is just okay. And this is what I recommend you do for your project. So if you have missing data, put in the put in the average. The exception is with the outcome. If you have missing data on your outcome variable, talk to me. We will have to work out whether it makes more sense to use the mean or, in that case, to just drop them. And that decision is analyst discretion. It depends on the context. It depends on the data. It depends on what you're trying to do. So missing on your predictors, use mean imputation. Put in the mean for that variable instead. Missing on the outcome, talk to me. And then the kind of state-of-the-art approach is something called full information maximum likelihood, which kind of in simple terms is like it tries out a bunch of different like what the value would be for the missing data, and then it gives you like a distribution of this is the likely effect, assuming these possible values of the missing data kind of thing. It's very computationally intensive. Excel can't do it in a simple way. The software that I have that does it is again the one that's like $1,000 kind of per person license. So yeah, there is a state of the art to this that is recommended for high stakes work. If the work is relatively low stakes, like our project, mean imputation is fine. Do not listwise delete. If you have missing on the outcome, talk to me. Talk to me. Questions about dealing with missing data? Okay, now we have zero inflated outcomes. So zero inflated variables are, I've mentioned this before, variables that have a lot of zeros, yeah? Sick leave, where a lot of workers don't go on sick leave. They don't take sick leave. They don't take personal leave in a given month. And so you have a lot of zeros and suddenly 1, 2, 3, 1, 1, 1, 2, 2, 2, 3, 3, 3. And so it's zero inflated. You can see this with credit card interest, extremely common. So kind of invariably, 1 or 2 or 3 students every term kind of comes to me. They're like, yeah, I have zero inflated data. It's very common. It's almost never it's almost never covered in textbooks, despite how common it is. It's crazy. The thing that makes zero inflated data tricky, well, you'll see. I'll walk you through the two-step approach, and you'll see why we have to do this. We have to run 2 kinds of regression models. So let's go with the example of credit card debt. Yeah. So again, what does it mean for credit card debt as an outcome? And remember, we're talking here about outcomes. Yeah. What does it mean for credit card debt to be zero inflated? A lot of people have no debt. They pay off their credit cards every single month. Hopefully that's you. For some, they have some debt. Yeah. You have to run 2 kinds of models. The first kind of model predicts whether they have any debt or not. So you recode credit card debt as 0, 1. 0, no debt. There's 0. 1, they have any debt, whether it's $1 or $200,000. Oh, I think that's too much for a credit card. Anyway, it's yeah, you code it as 0 or 1, no debt or has some debt, and then you predict that outcome. Yeah, you use all the observations, and this regression model is predicting the presence or absence of debt. Then completely separately, a separate model, you take your data in step 2 and you go, these are the people with no debt, take them out for now. Keep only the people with at least a minimum of debt, at least 1 cent of debt, and predict amongst the people who have debt, what predicts who has more debt than others. Yeah, so we have step 1, predict who has debt and who doesn't. Step 2, among those who have debt, who has more and who has less. Yeah, and what you'll find is often you'll have different predictors. Some things will predict the presence or absence of debt. Some things will predict for those who have debt, those who have more, and those who have less. This is necessary because if you don't account for the zero inflation, your effects will be a kind of dog's breakfast mix of these two very different things and will not be interpretable. So if your outcome is zero inflated, do this. Step 1 and step 2. It really adds a lot of value to the modeling, where you're predicting who has debt, who has some, who has presence or absence, and who has more, who has less among those who do have presence of the outcome. Questions, class, about zero inflation. If you think you have zero inflated data, talk to me. Talk to me. Okay. Lastly, we get into model building. So remember how when we ran the power analysis, as we dropped predictors, we got more and more power. We can find smaller and smaller effects. This is why we don't chuck every predictor we can think of into a regression model, because the more predictors are in your model, the less power you have, or you are kind of hamstrung. You can't find smaller effects. And this includes the predictors that are not statistically significant. They kind of waste your statistical power. You're kind of wasting it on these effects that are basically indistinguishable from zero. Yeah. The predictors also soak up shared variance with other predictors in the model, that overlap that they have. So what we want is parsimony. We want a parsimonious model where it's small enough that we can interpret it, and we don't leave out anything that's statistically significant and meaningful. One way to do this, the easiest way, not the best way, but the easiest way, and what I recommend for this class, is stepwise regression. We're going to do this now with the car listings data. I think this is something that's best done. I'll do it and I'll explain it after I've done it. So here we have the original model. I'm going to delete a bunch of these extra worksheets here. Okay, we're back to raw. We're going to go back to car listings and we're going to do a stepwise regression model. Remember how I said you generally will have multiple regression models? This is why, because you may find yourself doing a kind of stepwise process. Our outcome here is list price. Our predictors in the X range are all of these. Let's not tick any of these boxes. Keep it simple. Okay, we have our regression output again, exactly the same as before. What we're going to do, class, is we're going to look for the p-value that is the highest, the least statistically significant, and we're going to not include that the next time we run the model. So here, the one with the highest p-value is photos. So now let's run the analysis again without photos. It's not statistically significant. We don't need it. It has the highest kind of p. It's the null is most likely to be true for that one. So let's run it without photos. So we're changing the X range, no longer including photos. Now we have our second model. Adjusted R-squared hasn't changed much. That's a good sign. Photos is no longer in the model. Has anything changed? No, this is years is still significant. Odometer is still significant. Seller private is not. Yeah, we're kind of in the same place. And we still have all these extra predictors not doing anything. So now we go, okay, what has the highest p-value here? Body type. Doesn't seem to be predicting. Kind of effect seems to be very close to the null. Let's remove body type from our analysis. So the easiest way to do this, pardon me, is to make a copy of the data. And in this copy, we remove the variables we don't want. Don't do this in your original data set because, because you might end up removing something. There you go. I deleted color by accident, right? So it's Good to always keep a version of your data where everything is in it. Okay, so now we run analysis without those variables that we don't need. Now we have a much more sparse model, fewer predictors. Only have 4 years, odometer, seller, color. Okay, years and odometer still playing a big role in the predictive model. R square is still great. We're looking good. Color blue is not adding much. Let's drop it. So we run the model again without blue. We change the predictors to just these 3. Run the model. Wow, there we go. Not much has changed. Adjusted R squared again, still very similar. And seller private is still not statistically significant. Granted, we don't know if this is because of power but we can't do anything about that, right? We have the data we have. We can't add to our sample what isn't there in this instance. And we can kind of just shrug our shoulders and go, maybe it's really 0. Maybe there's not enough power. We don't know. So here it's up to you what you want to do, if you want to keep it in the model or not. If you kind of go, yeah, no, let's be conservative, let's not keep it in, then you run your final model, where for your predictors, you only have odometer and years. Oh, why is that? Input X range. Okay, let's do that again. Regression. Okay. There we go. The final model. Everything is statistically significant. Adjusted R square. Again, has not changed much. The other variables were really not lifting much weight. It really was just model year since 2000 and the odometer. And yeah, that's your final model. So when you kind of put together your predictive model, you'd be working with this. When you present your results, you can choose to report the ones that were not statistically significant if that is of consequence for what you're trying to do and you're kind of going, yeah, this doesn't matter, that doesn't matter. If that is important. If it's not, then you kind of really pare it back to these are the 2 consequential variables and this is why they matter, and then you proceed from there. That is stepwise regression. You're dropping variables one by one based on their p-value, and you retain the variables that are statistically significant, and you stop when everything is statistically significant. This practice is okay. The trouble is it has a risk of overfitting. We covered this last week. Overfitting is where your results are a little too strongly and tightly fit to your sample and doesn't generalize well out of sample. So what I did with the stepwise regression, that is the very simple way to simplify a model. If I wanted to do this in a principled way, I would use, again, these machine learning techniques. Lasso especially is fantastic. So if you're doing this kind of in a high stakes setting, use Lasso. For what we're doing, stepwise is okay. But it does have this risk of overfitting. Questions about model building class. I expect you to do this for all of your regression models, by the way. You will be doing some model building. If you keep variables in the model, have a good reason for it. It should be part of your storytelling. But if they're not kind of adding value, you don't need them in the model. They're just soaking up statistical power. They're just they are wasting space. Okay, we're nearly done, class. 8:45. This is one of the longer and tougher lectures. Thank you for powering through. Sanity checks. So there are many sanity checks to check that what you're doing makes sense. I'm a big fan of getting qualitative data whenever possible to verify, triangulate that kind of what I am doing with my numbers matches kind of what people are saying largely. one thing that's super handy is something called leave one out. So this is where you kind of go through your data. You're really intimately familiar with your data, and you go, I don't know about these three observations. Like, should they be there? Should they not be there? If And you're like, are these observations really affecting my sample? So what you do is you try running the model, leaving one by one out these kind of predictors that observations that you think are maybe influential, that you think are biasing the sample. And if leaving them out has a substantial impact in your results, you kind of go, I don't know. I don't know if I can trust this. It then it is a question of should that observation be there or not. And if you can't come to a principled answer, don't rely on the data. It's not giving you a clear answer. If a Lou analysis dropping observations that are influential has a noticeable impact on the R square, on the B coefficients, whether they're significant or not, if it has this very noticeable impact, you kind of go, oh, I don't know. I don't know. This is why I like having the qualitative data is if I do this Lou analysis and I get something concerning, I can kind of go, yeah, in this instance, the quant data can't give us something we can trust. We're going to go with what the qual says just as a starting point and go from there. It's look, I've been saying from week one, right? Like you can't always be relying on data analysis. Sometimes the data that you have are simply not probative enough. They simply do not like unequivocally say kind of what the effects are and what is consequential, what is important. Sometimes your results are not robust. They're not robust because when you drop a variable, everything changes. Sometimes they're not robust when you drop an observation, everything changes. When that happens, you kind of go, no, something isn't right. I'm not sure these results are stable. That's the word, that's the language I use. Are the results stable? Are they robust? And if they're not, don't trust them. Plain and simple, don't trust them. And then the boogeyman, the cause of maybe the most tears working on the project, Nosferatu himself, the suppression effect. So this is what happens when you have very, very concerning multicollinearity. You run your regression model and you come to me and you say, Raj, this predictor is supposed to be really important, a positive predictor of my outcome, but it's negative. The sign is all wrong. That is suppression. Yeah. So a very problematic suppression effect is when your B coefficient, let's say the effect of the odometer kind of reading on price, is the opposite of the correlation. So they go together when they correlate. But in the context of the full system of predictors, in the context of the full model, in multiple regression, the sign flips. That is very problematic. And I see it every year, every term. I see this in projects. A somewhat problematic, but not as concerning, is when the beta coefficient, the standardized coefficient, is substantially larger than the correlation, where like when you have a bunch of predictors, it's activating other predictors and making them work. This is not super concerning. It can be like mystifying, but it's not problematic. So yeah, I'm gonna focus on the very problematic case here, where you run your regression analysis, your variables are so correlated, so overlapping, that the sign of the relationship flips when you put it in a regression model. This is suppression, and this is it really complicates things. So when you have what I'm calling here very problematic suppression, beta polarization, the B coefficient flips in sign. It's not what it should be. It's the opposite of what the correlation shows that it is. Do not interpret your regression at all. Just stop. Just walk away and figure out what's happening. And what is happening is severe multicollinearity. Yeah, is some of your predictors are overlapping so much that it's completely overturning the direction of the effect. And you have to figure out which predictors are driving the suppression effect. And so this begins a whole complex kind of rigmarole of dropping variables, adding them in. What if I drop this? What if I add that? I've had students tell me they spent the whole day just adding and dropping things to see what's driving the suppression effect. It can be, when it happens to you, it can really stymie you. It can really uh, complicate your life. This happens quite a bit. Most student concerns tend to be like, if it's zero inflation, usually it's not so much concerning as it's an opportunity to explore really interesting patterns in the data. With suppression effects, it's just like, oh God, make it stop. So when I encounter suppression effects in my consulting, I have to stop and go, we're doing this all over, rethinking the model. Or sometimes, if there are only one or two suppression effects, I kind of don't interpret the suppression effects. I kind of go, nope, there's suppression effects. Those are not stable. I'm not going to interpret them. I'll interpret everything else. But that depends on what the suppressors are and how many there are, and my own subject matter expertise of, I know that this variable is not super consequential anyway, and it's being suppressed. So yeah, it doesn't particularly matter. You're gonna have to make these calls on your own. I mean, I'll be there to help. But yeah, suffice to say, if you have suppression, talk to me. And yeah, that is all I have for you. You have gotten through maybe the most technical lecture of the term. And now you know just about everything, other than the causal side of things, which we'll cover next week. You know just about everything you need to know to do the project. You are good to go. Class, thank you for sticking around. Thank you for bearing with me, being away, dealing with this sprained ankle. I am hoping to be in with my moon boot in a week. And if you have any questions in the meantime, please reach out. When we see each other next week, I'll be handing back your exam scripts as well, your quiz scripts, I should say. Yeah, that's it. That's all I have.
Thank you, Raj.
No worries. Thank you.
Thanks, Raj. Have a good night.
Thanks, Raj.
Thank you. You too.
Thanks.